This is just a quick walkthrough of the answers to the problems that we did in class. These are the notes that we went through in class. The speed of the wave is a factor of wavelength and frequency, but because the speed of light and electromagnetic waves is a constant, that means that we already know the speed part of the equation, and therefore, if we know either the wavelength or the frequency, we can calculate the missing value. And in the same way, the formula for energy has a constant value called Planck's constant, and so the energy equals Planck's constant times the frequency. So since we know what Planck's constant is at all times, that means that we know how to find the energy given the frequency, or we could also use the energy in Planck's constant to find the frequency. So we're going to walk through a few questions with these formulas. So the two formulas are the wavelength times the frequency equals the speed of light, and the energy equals the frequency times Planck's constant. So everything we do, with the exception of one question, everything we do in this set of problems is a variation of those two formulas, or sometimes a combination of those two. So what is the frequency of light whose wavelength is 4.257 times 10 to the negative 6th centimeters? So a couple things on this one. First of all, it gives us the length in centimeters. So I'm going to go ahead and convert that to meters. And the question is, what is the frequency given the wavelength? So we're going to use the speed of light equals the wavelength times the frequency formula, which means that the speed of light divided by the wavelength equals the frequency. Okay, that's just rearranging the equation, divide both sides by wavelength. The speed of light, 3.00 times 10 to the 8th meters per second, divided by 4.257 times 10, and it's actually going to be the negative 8th, right, because centimeters are 1/100th of a meter. So in order to convert it to meters, I divide by 100 or move the decimal point 2 places over, and that gives us a different exponent. And from there, the meters are going to cancel each other out. We do the division using the calculator, and the result we get is 7.05 times 10 to the 15th hertz, or cycles per second. Okay, so this is your final answer down here. Determine the energy. Okay, so now we're doing the energy, and the energy is Planck's constant times the frequency. We're given the frequency here. So we have the frequency. Planck's constant is a constant value that we know. So we just multiply those two values together. So the energy is Planck's constant, which is 6.626 times 10 to the negative 34th. The unit is joule seconds. And that's times the frequency, 3.55 times 10 to the 17th hertz, or cycles per second. When we multiply those together, we end up with 2.35 times 10 to the negative 16th joules. All right, so this is the one it's a little bit different. It's asking for time in seconds, and it gives us the distance. It also gives us the frequency, but we don't really need that. So what we're going to do is the time is equal to the distance divided by the speed. Right? So the distance you're traveling divided by the speed at which you're traveling will tell you how long it's going to take to get to cross that distance. So in this case, the time equals the distance, and again, I'm doing a little conversion here, 8.00 times 10, and it'll be to the 10th meters. Oops, not kilometers, meters. divided by the speed, which is the speed of light, 3.00 times 10 to the 8th meters per second. And when you divide that out, you actually come up with an answer of 266.67 seconds. So it takes 266 seconds for light to travel from Mars to Earth. Okay, so the speed of light, which we know is 3.0 times 10 to the 8th meters per second. What is the wavelength if the frequency is given here in hertz? So this is the speed of light equals the wavelength times the frequency, or the speed of light divided by the frequency equals the wavelength. So we're going to plug in 3.00 times 10 to the 8th meters per second divided by 7.500 times 10 to the 12th hertz equals the wavelength, or the wavelength equals 4 times 10 to the negative 5th meters. Okay, what is the frequency? Okay, so here's one where we're going to be using the energy equals Planck's constant times the frequency. But in this case, they gave us the energy here, and they want us to find the frequency. So we're going to do the equation like this. Energy divided by Planck's constant equals frequency. The energy is 1.55 times 10 to the negative 24th joules, and the Planck's constant is 6.626 times 10 to the negative 34th joule seconds. That's going to equal the frequency. The frequency, when we do the math, comes out to, in this case, 2.34 times 10 to the 9th hertz, or cycles per second. All right, so this is a two-part question. It's giving us the energy, okay, the joules, the unit joules, capital J is always energy. And it's asking us two questions. First, what is the frequency? Second, what is the wavelength? So we're going to use both equations in this problem. We're going to start with the energy divided by Planck's constant equals the frequency. So the energy is 3.37 times 10 to the negative 19th hertz, joules. And then that's divided by Planck's constant, 6.626 times 10 to the negative 34th joule seconds, and that gives us a frequency of 5.09 times 10 to the 14th hertz. Okay, now we know the frequency, so that was part A. All right. Second part is, what is the wavelength? Well, now that we know the wavelength, we can use the speed of light divided by the frequency to find the wavelength. We didn't know the frequency before, but now we found it using the energy equation. So now we're going to plug in the answer we got here into the second equation to find the wavelength. So 3.00 times 10 to the 8th meters per second over 5.09 times 10 to the 14th hertz equals the wavelength, which is 5.89 times 10 to the negative 7th meters. So that's the second part of the question. So the first part was the frequency, which was here, and then we used that frequency in this equation to find the wavelength, which is here. Okay, so the yellow light has a wavelength of 589 nanometers. So this is another one where we're going to do a quick conversion. If you didn't do this conversion, you probably got the same number that I'm going to get at the end, but with a different exponent. So 1 nanometer is 1 times 10 to the negative 9th meters. So anytime you get a question that gives you nanometers, all you have to do is take the number, and then that's going to be times 10 to the negative 9th meters. That's all you have to do for the conversion. You don't have to move the decimal point because you're going to plug it into your calculator anyway, and your calculator will take care of adjusting that when you get your answer. So this is the speed of light divided by the wavelength is going to give us the frequency. So 3.00 times 10 to the 8th meters per second divided by the wavelength, which is 589 times 10 to the negative 9th meters. Again, if you just wrote 589 on the bottom and did the division that way, you will probably get the same number that I'm going to show you for the coefficient, but with a different exponent. So it should come out to 5.09 times 10 to the 14th hertz frequency, cycles per second. If you didn't do that, you would have gotten something like 5.09 times 10 to the maybe 6th, okay, something like that, or 5,090,000 or something like that. So if that's what you got, it's just because you didn't do this conversion up here with the nanometers, and that's not the end of the world. You just have to keep track of what units you're using. Okay, here's another wavelength with the wavelength given in nanometers. So I'm going to do that conversion in a second, but the question is, what is the frequency? So speed of light divided by wavelength equals frequency. 3.00 times 10 to the 8th meters per second divided by the wavelength of 640 times 10 to the negative 9th meters. Again, that's just the conversion from nanometers to meters. It's a 9. Divide that out, and we end up with 4.69 times 10 to the 14th hertz. Okay, so again, if you didn't do the conversion, you should have gotten something that looks like 4.69 or 469,000 or 4,690,000, something along those lines, or which would be 4.69 times 10 to the 6th, I believe, might be what you got. That's just because you didn't do the nanometers to meters conversion. All right, here's another one, and there was a formatting issue on the sheet. This looked like it might have said 106, but it's actually 10 to the 6th. Mega is million, so 10 to the 6th. So one more time, if you didn't catch that or ask about it, I know some of you asked in class, again, you might have gotten the same number, but with a different power of 10. So this is giving the frequency, asking you to find the wavelength. So speed of light divided by frequency equals wavelength. 3.00 times 10 to the 8th meters per second divided by 103.4 times 10 to the 6th hertz gives you 2.9 meters, or 2.9 times 10 to the 0 meters. It's a 0. Okay, and then the one. Okay, we have the frequency and asked to find the energy. So this is a straightforward energy formula problem because we're given the frequency, and energy equals Planck's constant, 6.626 times 10 to the negative 34th. The unit is joule seconds times the frequency, which in this case is 4.69 times 10 to the 14th hertz. And when we calculate that, we end up with 3.11 times 10 to the negative 19th joules. It's a 19. Okay, so that's that was the last one on the sheet. Again, they're all variations on either the speed of light equals the wavelength times the frequency, or the energy equals Planck's constant times the frequency. In each equation we have one given, one constant, either the speed of light or Planck's constant, which are constant values, and then you have to determine the missing value, because you'll either be given, in this case you either be given the wavelength or the frequency, or in this case, in the bottom equation, you might be given the energy or the frequency, and you have to work it out. Other things to be aware of, again, are the conversions between things like kilometers, nanometers, meters, centimeters, all those. Make sure you put your scientific notation in the calculator correctly, and then if there's a problem there might be problems that have you work between the two equations, for example, using the wavelength to find the frequency and then the frequency to find the energy, or as in one of the examples on this page, it gave you the energy to find the frequency and then the frequency to find the wavelength. So those might be different issues that you could have come up in these types of problems.